Okay guys, so for this first problem, finding the domain, we're literally trying to find all of the x values that are possible. What are the x values that we can plug into this function such that we'll get legitimate y values? And the way that we go about finding that is by figuring out what the restrictions are. So we got one restriction down below, x minus 7. That cannot be equal to 0. That's where we'd have division by 0. And then the square root of x plus 3, the square root, that has to be, what's underneath the root has to be greater than or equal to 0. So we set these things up and we solve, and we end up getting our solution here. Let me go ahead and show you the graph. So here I got the graph shown, and we can see here that we start off, well, we can't really see it, but if I hit the trace button and scroll to the left, we can see that I have x values all the way up until past the -3. And past the -3, we don't have any x values or any y values because we end up with the square root of a negative underneath that root there. So we're not given any legitimate y values when we plug in x values that are outside of the domain. So let's move to the next problem. Okay, so our next problem is literally just the opposite of domain. We're trying to figure out all the legitimate y values. What are all the y values? And I will let you use a calculator to solve this question, but you should know that you do have some tools to graph this, and so you should know a few things. For instance, that we have a horizontal asymptote at 2. I have a leading term in the numerator that's a 2x to the first, and a leading term in the denominator that's a x to the first. And as a result, we would end up with a 2 for our horizontal asymptote. So that kind of tells us something about the range of values. Alright, so here is our graph that shows the rational function. And one thing that I can do to see what my range of values is play around with that trace button. If I hit trace and scroll to the left and the right, if I scroll left here, I would see that I'm approaching some value, getting closer and closer and closer to some value. And I can hypothesize that that value is going to be 2. In fact, based on what I know about the horizontal asymptote, I can say, oh yeah, it looks like it's going to go to a 2, but it's never actually going to quite get to 2. In fact, if I were to plug in 2 into my y value and try and solve for x, I would end up with a statement that doesn't make any sense, and I would have to exclude 2 from my range of values. So our range of values expands all the way from negative infinity to 2, then 2 to positive infinity, not including that 2. Let's see what's going on with problem number 3 here. Okay, so problem number 3 deals with increasing, decreasing, and the thing about increasing and decreasing is you have to look at what's going on with your x and your y value to see whether the function's increasing or decreasing. For instance, if you have a positive change in x and a positive change in y, that means that you have an increasing function. A positive change in x and a negative change in y would be a decreasing function. I kind of think of it like a negative slope and a positive slope. Increasing is a positive slope, decreasing is a negative slope. And on this particular function, if you trace, anywhere you trace, you see that for a positive change in x, you have a negative change in y. So this function actually decreases on the entire function. Every time x gets bigger, y gets smaller. Okay? So there's actually no increasing function here. It's decreasing for the entirety of the function. Alrighty, so for our next problem, we want to find the vertical and horizontal asymptotes using limits. So let me address the horizontal to start off. Here's a picture of our graph, and as x, this should say down below, this should say as x goes to positive and negative infinity, then the y value will go to a 1. And you could see that using the trace feature. You could also see that just by looking at the leading term in the numerator and denominator. They have the same degrees, so they all cancel out to give a 1. You have a horizontal asymptote at 1. As x gets bigger and bigger and smaller, overall your y value is just going to approach a 1. Now the vertical asymptotes are where we have division by 0. And the vertical asymptote, we have to address what's happening as we approach the vertical asymptote from the right side and the left side. That's what the positive in the upper right hand corner and the negative in the upper right hand corner means. So as we go to positive 4 from the positive side, we go up to positive infinity. As we approach 4 from the negative side, we go down to negative infinity. And the same is true for negative 4. Well, the same principles apply. All right, so this next one's kind of a large problem, and I'm not going to do it for you. It's really a problem that involves a lot of algebra. And however, you have to get the setup right. To prove two functions are inverses of each other, you have to plug one function into the other and get an x. F of g of x is equal to x, and g of f of x is equal to x. And then from there, it's a matter of using algebra skills in order to come up with that x value. So if you need help with that, I'll answer your questions. The next one, we're given a function, we want to find the inverse. To find an inverse function, we flip our x and our y value, and we solve for y. And so what I did here is I flipped x and y and solved for y by first multiplying both sides by the denominator, and then pull the y terms to one side, factor out a y, and then divide both sides by what's in the factor there. And that gives us the y all by itself, which is shown as g inverse of x. Remember that you can check whether two functions are inverses of each other by graphing them, and if they are symmetric over the line y equals x, then you see two inverse functions. So our next problem here, you really have to understand transformations. And so we have to figure out how to transform this graph based off of this transformation here. So what I did is I labeled the points of f, and then I tried to figure out what's going on with each one of these transformations here. And you have to remember that whenever you add or subtract directly on the x, it does the opposite of what you think. The plus means you shift to the left one. That's why I have x minus 1. And then if we were to subtract, that means you would move to the right. The 3 is a vertical stretch by a factor of 3. The 2 is a vertical shift up by a factor of 2. So we really have to understand what a transformation will, how that will affect the graph. So our next one here, we want to complete square and right in vertex form. Well, let's see here. To write in vertex form, to complete this square, we need to mess with these x terms. So the first thing that I did is I grouped the x terms together and I factored out a 2. And then the next thing I did is I completed the square by taking half of the term next to the x, the 3, and raising it to the power of 2. So 3 over 2 squared is 9 over 4. So you'd say, okay, well, we're changing by adding a 9 over 4, but actually, we're multiplying the 2 times the 9 over 4. So we're actually changing that by like a 18 over 4. And so we need to negate that over here. So I subtracted 2 times 9 over 4 here. This is the same thing as subtracting 18 over 4. And then what that did is that gave us a perfect square trinomial on the inside of the parentheses, which I factored and then wrote into a binomial squared. And then I started getting a common denominator, and then finally the vertex form is shown here. One thing that you could do to make sure that you're right is you could graph both of these functions, g of x, on the calculator, and if they show you the same exact graph, then you know you're right. So our next problem here, we want to find vertex form using a different method, using negative b over 2a. That will give you the x value of the vertex. So that's what I did first. I found the x value of the vertex, and then I plugged in the x value of the vertex into the function to find the y value of the vertex. Once I did that, I used the general form of the vertex form of a parabola, plugged in my hk and my a value, and that was it. I didn't have to solve for a because I have that from the very get-go at the beginning there. Alright, I'm starting to jam a little bit because I'm getting nervous about the time. I think I might have to make a second video. Alright, this next one we got to sketch the graph. Well, the first thing we know, based on what we have here, is that we have zeros at a 2, at a 4, and a negative 1/2. And if you know the zeros, you are halfway there, right? You could literally plot each one of your zeros and then plug in an x value prior to like negative 1/2, and you'd see that you have a y value up here. Plug in an x value in between negative 1/2 and positive 2, and you'd see that you have negative y values down here. Plug in an x value in between 2 and 4, and you'd see you have negative x values. Y values, excuse me. Plug in a x value after 4, and you'd see you have positive y values up top there. So you could literally just draw your graph by plugging in x to see what y is. That's the easiest way. Well, it's the tried and true way. What would be easier is to understand what this function is doing with ending behavior after you graph your function, and multiplicities. So ending behavior, if I were to multiply all these binomials together, I would see that I have a leading term that is a positive 2x to the 4th power, and that tells me that I have ending behavior as x goes to infinity and negative infinity, y will go to infinity. So that tells me what the ends are doing there. And multiplicity, even multiplicity, tells me I bounce off the x-axis. So right here at 2, it has a even multiplicity, that's why I'm bouncing right here. The other ones are odd multiplicities, that's why they go right through. So we can really approach that one in a bunch of different ways. Remember, it's not magic. Plug in x, you get y, and that will tell you for sure what the graph should look like. The other things are extras, so that you don't have to always plug in x and get y. You can look at the patterns to understand. So this next one, we want to see what the function is doing. We want to find the cubic function in standard form with the table of values. Well, we have these x values that give us y values that result in 0. So that gives us 3 factors. If we know the zeros, we know the factors. And then we have this other one here, and when negative 1 is x, y is 24. That is there to tell us what the possible a value is. Remember, you can have a bunch of different functions that go through the same roots, but you can have some vertical stretching or some reflecting that will change the function. So that's what I did. I plugged in a negative 1 and a 24, and I solved for a, and I found out that a is a 2. And then from there, it's just a matter of multiplying my binomials and my a value together to get the function in standard form. Alright, so this will be the last one for this segment. We want to list all the possible rational zeros and find all the real zeros. So first of all, the possible rational zeros are found by taking the factors of the constant and dividing them by the factors of the leading coefficient. So that gives us a total of 6 possibilities. And then from there, I would literally have to synthetically divide with all those possibilities to find which ones are actual zeros. But let's say we've eventually arrived at 4 being the real 0. And we know that because I have a 0 right here, that's the remainder. And then that tells me that I have, this is my factorization so far here on the right. And then we can synthetically, we don't need to synthetically divide. We have a quadratic. And so what I did is I set that quadratic equal to 0 and solved for the roots. And based on those roots, I could rewrite the, I don't even need to rewrite the factored form. I just needed the roots. Okay, I'm running out of time, guys. Sorry.